Welcome to episode 35 of Behind Our Science. We're very excited today to have a very special guest celebrating Black History Month with us. We want to welcome Dr. Dennis Jones. He's an associate professor of pathology and laboratory medicine at Boston University's Chobanian and Avedisian School of Medicine. Okay, I made it through that. That was great. A distinguished leader in cancer research, he was recently named the recipient of 2026 ASIP Cotran Early Career Investigator Award. Congratulations. His lab is currently focused on how tumors manipulate blood vessels to escape the immune system, developing new strategies to help immune cells better infiltrate and fight metastatic breast cancer, and a lot more that we're going to learn about today.
Welcome, Dennis.
Thank you. Thank you for having me.
Yeah, we're very excited about this episode. We always try to showcase at least an ASIP member, but in your case, your science is fantastic and it resonates with a lot of our listeners. We have a lot of people that work in cancer, but also in pathology overall. So that's great. So we're going to start with the first question, Dennis. And do we know that your lab focuses heavily on the tumor microenvironment? And so that's a word that not a lot of people are used to. So for our listeners who might picture cancer as just like a clump of bad cells, can you explain what a microenvironment is and why it is just as dangerous as the cancer cells themselves?
Yeah, so the tumor microenvironment is basically the ecosystem around the cancer cells. So if you think of a tumor as a wound that never heals, there are cells that come in to repair the damage, but those cells are repurposed to actually help the tumor progress. And so some of those cells in the microenvironment include cancer-associated fibroblasts. So fibroblasts normally rebuild tissue like in a wound, but in tumors, they lay down this dense extracellular matrix, these secreted proteins such as collagen. And these fibroblasts also secrete suppressive factors that block T cell function, so immune cell function. Some other cells in the microenvironment include macrophages. So think of macrophages as cells that eat things. So they normally clear debris and they repair damage as well. But in tumors, these macrophages are hijacked as well. They become pro-tumor. They promote new blood vessel growth and remodeling of the matrix that I just mentioned, and also they can suppress immune cells. Cells that we are interested in my lab also include T cells in the microenvironment. So T cells, I'm not going to get into the types, but they are of significant interest in the cancer field because they can kill abnormal cells, including cancer cells. But in tumors, these T cells are often not present or they are dysfunctional. And then finally, another cell type I'll mention are blood vessels that are made of cells called endothelial cells. And you need blood vessels to deliver nutrients to all tissue. But in tumors, these blood vessels are abnormal. They're like very leaky. So when you don't get enough oxygen in the tissue becomes hypoxic, and this actually leads to a sequence of events that further promotes immune suppression in tumors. So I would say that because this tumor microenvironment actively supports tumor growth, invasion and metastasis, and also immune invasion, targeting this microenvironment is almost as important, or maybe as important, as targeting the cancer cells themselves.
Thank you. That's great.
And one last thing, while all these cells matter, my lab, we've primarily been focused on the tumor blood vessels, as you mentioned, and how they are impaired.
Okay. Yeah, no, that makes sense. Like, it's sort of, if you think about warring kingdoms, if you cut off their access to resources, it's going to be harder for them to survive. That's really good. And thank you for not going into all the different types of T cells. I'm not sure that my computer has a bandwidth.
No, everyone's
for that episode.
Yeah. We all are thankful for that.
I mean, I'm sure it's fascinating, but as I've seen, it's like an ever-ending scroll of different types of T cells that exist now.
Yeah, I think I don't I'm probably behind on all the subsets that exist.
Yeah, I pray that I always am
Oh.
behind and that I'm not at the forefront of that.
I got to catch up. I have an immunology class to teach later, well,
Oh,
next month. So,
oh, okay. You have a month. You got some
yeah.
time. So one of the intriguing discoveries that you've found is solid stress, this concept that tumors compress their own blood vessels. And how does this crushing force prevent our immune system, specifically the nameless T cells that we're not going to get into, from functioning properly? Like you mentioned, they start malfunctioning. And how did you uncover this mechanism?
Okay. So solid stress was first identified by Rakesh Jain at Mass General.
Sorry. Thank you for correcting me. I appreciate that.
No. I'm just giving some context. So he was actually my co-mentor when I was a postdoc there at Mass General. And so we met every Friday, and he reviewed my data as it came in. And it was actually his insight that helped point us towards this mechanical explanation for what we were seeing. And so his group, Dr. James' group, first reported solid stress in tumors about 30 years ago. And they published the first quantitative measurements of these forces around the time I began my postdoc. And so, as you mentioned, solid stress is this mechanical force. It's generated by the tumor's solid components, such as the proliferating cancer cells, the stromal cells, like I mentioned, those cancer-associated fibroblasts, and the extracellular matrix that they secrete as the tumor grows. So Dr. James' work showed that these forces can physically compress blood vessels and lymphatic vessels in and around tumors, and that leads to reduced oxygen and drug delivery and keeps immune cells from reaching cancer cells. And so we kind of stumbled on this mechanism as we watched tumors grow inside lymph nodes. When we used this tiny window, we called it a lymph node window, that allowed us to perform real-time imaging on the lymph nodes and the tumors in those lymph nodes. And we can image the vasculature in the lymph nodes as those tumors grew. And we saw that the blood vessels became compressed and they had less blood flowing inside them. And so we asked if that translated to any effect on the presence of T cells and B cells and lymph nodes, because blood vessels in the node are important for T cell or lymphocyte entry into the node. And we saw something surprising that even though lymph nodes, we think those are the sites of immunity, they're usually packed with immune cells like T and B cells, but the metastatic tumors inside them had almost no T cells. And so it turned out that the tumor acts like a growing object that physically like squashes the blood vessels that normally let T cells enter. And we showed the same effect by gently compressing the lymph nodes with a small device that in collaboration with an engineer. And we could partially reverse this compression with a drug called losartan. And so most people know losartan as an antihypertensive, but it also has anti-fibrotic effects that reduces the deposition of that extracellular matrix. So when you reduce that matrix, it can decompress the blood vessels, making them more functional and allowing T cells to get in, and that's what we saw. So we think this strategy might improve immune therapies because for these therapies to work, T cells have to get into tumors. Sorry, that was a long answer.
No. That's perfect. Thank you so much.
No, I think that's great. It's a great answer. And I mean, I'm a cardiovascular scientist, so I mean, this is really exciting, especially the losartan story. I mean, I read about it from your papers, and so I understand a lot of that pressure and how it becomes evidently significant for treatments that are ongoing in the medical industry. So let me twist it a little bit into and going back to the cancer area. And that's because a major challenge in cancer therapy is metastasis. So a lot of people that might not be familiar with this is when cancer cells spread to other organs, not the organ that they originally originated from. So your lab looks at how cancer persists in these new locations. So why is it important or why is it hard for current treatments to find and eliminate these cells when they've left the primary site?
Yeah, so I mentioned lymph nodes. So lymph nodes are a common site of metastases, and that's one reason why we studied lymph nodes is because, we wanted to see how cancer behaves once it leaves the primary site. Um, so we're interested in metastasis because that is usually what people die from metastatic disease. Although not particularly lymph node metastasis, but other organs like lung and liver. But we thought we could get some clues from studying the lymph node. So you said, why is it important or hard for current treatments to
Yeah.
eliminate metastases? So there are a few reasons. First, metastases can hide in places that are difficult or risky to operate on. So doctors can always remove, surgeons can't always remove them or sample them easily. And second, each tissue, such as lung, liver, bone, lymph node, has its own local environment or microenvironment, as we talked about, that can actually protect and nourish the cancer cells. And they might behave differently than they do in the original tumor because of this different environment. And so you probably have heard about drugs that try to starve tumors by blocking growth of new blood vessels.
Hmm.
And so that idea makes sense for many primary tumors, because these primary tumors known for decades now that they build their own blood supply to keep growing. But what we found when this was some of my postdoctoral work, we found that at least in lymph node metastases, these metastatic tumors don't need to make their own blood vessels. Instead, they grow by using the rich network of blood vessels that the organ already has. And so, because these metastases don't rely on forming new blood vessels, therapies that block blood vessel growth don't work to stop metastatic growth, at least in these organs. And we saw this in our animal models and in patient data for breast cancer that had spread to lymph nodes. And since this finding, other teams have reported the same thing in other cancers, such as liver and kidney cancer. And so, I guess the take home here is that some metastatic tumors behave differently from primary tumors. So we need treatments designed specifically for like non-angiogenic metastases rather than assuming one approach fits all, and that can be extended to other therapies as well.
Great answer. Thank you.
Yeah, that was beautifully put. It makes sense. Biology is not a single smoking gun, I guess, when it comes to treatment.
Go figure, right? Yeah.
So earlier you mentioned that you collaborate with engineers to mimic the compression in these metastatic tumors that form in lymph nodes of the vessels. How important is it for modern biologists to think like engineers when it comes to problem solving, like your idea or your concept of vascular compression?
I see. Yeah, let me see. I guess I don't know how an engineer thinks, but I can kind of generalize. But I think it would be useful for us biologists to think like an engineer to tackle these problems such as vascular compression. I assume from my observations that engineers they bring this solution-focused mindset to biological complexity, and that's usually complementary to biology. And so, as biologists, we are trained to observe systems, discover mechanisms, and ask how does this work or what happens when it doesn't work. And so, an engineering approach adds additional steps like quantifying the relevant physical parameters, and which I honestly hadn't thought of for that project. And then engineers can also model how these parameters change the system, and design controlled perturbations or devices to test causality or fix the problem. And so there are some things that we share, some core habits that we share, like we quantify our observations, we test how one variable changes an outcome. and kind of iterate our hypotheses. I would say traditionally, as biologists often approach problems through a biochemical lens, asking which molecules and signaling pathways are responsible. But in the case of this vascular compression project, however, the key variables were the physical forces that needed to be measured and manipulated. So I think all this just shows the power of multidisciplinary work, bringing new methods, perspectives, and outside expertise. Yeah, so this is an example here where the engineering approach truly complemented the biology.
Definitely. Yeah. And I will say that I'm not sure I could ever retrain my brain to think like an engineer, but it seems like collaborating with them is the way to go.
Yeah, collaborate. Yeah.
I think that's the best approach, right? I mean, we want to engage people with multidisciplinary approaches, but sometimes it's easier to just um, be everything, but it's really hard to do that. So, yeah.
Exactly.
Yeah.
Yeah.
No, thanks for that. So moving forward, I mean, a lot of these have translated into awards that you have been able to receive. First of all, congratulations on being named a Biden Cancer Moonshot Scholar.
Yeah.
When you look at your work on vascular therapies and immunotherapies, what is the dream scenario for how this translates to a patient, meaning a patient that's sitting in a clinic, let's say 10 years from now?
Mhm. Yeah, thank you. For some background, the Cancer Moonshot Scholars it consisted of early career researchers from across the U.S. who bring innovative approaches to cancer prevention, treatment, and diagnosis. And so that cohort of scholars was part of a larger effort, Cancer Moonshot program by former President Biden to accelerate progress against fighting cancer. And so I guess my work fell under the treatment arm of that, since we don't really work on prevention or diagnosis. But kind of along those lines, 10 years from now, I guess my scenario for translating this to patient is that I don't want stage 4 breast cancer to be like a death sentence, given the poor overall survival of people with um, advanced disease. And that's what our work is modeling. We're modeling advanced disease, particularly metastatic tumors that, as we talked about, physically compress and deform host organs, leading to death. And so uh, we want our goal is to restore vessel function so that drugs and immune cells can reach cancer cells. And so building on the work of Rakesh Jain, who I mentioned earlier, we believe that improving blood vessel function might be one avenue to increase the delivery of therapeutics and permit more T cells to enter tumors. But entry alone is not enough. So T cells must remain active when they're inside this hostile tumor environment. So my lab is now focused on uncovering some of the molecular barriers that suppress T cell function once they are in the tumor. Um, so you probably heard of these drugs called immune checkpoint blockers. So they remove inhibitory signals from T cells, allowing T cells to be more active. But they work on it only in a minority of breast cancer patients. And so we want to be able to identify and target specific tumor features that prevent eradication of those tumors. And so, stepping back from this immune-centric approach, my hope is that collectively, 10 years from now in the field, we'll have identified additional organ or site-specific vulnerabilities for cancer cells to target. So, since biopsies are not always feasible, particularly for metastatic disease, I hope that there would be circulating biomarkers that will be identified that report those vulnerabilities. And so I think this knowledge, 10 years from now, would allow clinicians to treat the patient accordingly and hopefully more effectively than the drugs that exist now for advanced breast cancer.
Wanted to take the time to talk about publishing pathways for some of the journals that we highlight. The importance here is that you take advantage of their major perks and their focus, because this also highlights a lot of the scientific communication that we broadcast. For example, the American Journal of Pathology focuses on experimental pathology with major perks as a high impact journal. Then also the Journal of Molecular Diagnostics, another great journal for biomarker validation, diagnostic assay development, but also they have major perks for rapid publication online. And last but not least, the Journal of Histochemistry and Cytochemistry, which is again focused specifically in advanced microscopy, spatial biology, and cellular structure. We've included a lot of the information in Spanish, English, and Portuguese, so take advantage of these journals and submit your science.
All right. So science is full of failure before success. As many of our listeners are aware, we do talk about the pitfalls of science a lot. Was there a specific failure in the lab or as you were preparing these studies where you realized you had an opportunity for growth or a major learning moment?
Yeah, that's a great question. I can't point to one dramatic, defining failure of my career or my, time in lab. But I think it's more of an experience of day-to-day, a steady stream of day-to-day setbacks, like experiments that don't work. And now as a PI, grants that aren't funded, papers that don't get accepted. And so over time, I learned that those outcomes are part of the nature of the job, and they're not a reflection of, personal failure. So in other words, I have to remind myself that I myself am not a failure because of these setbacks.
That's perfect. Yeah, a failure does not mean you're a failure. It's just it didn't happen.
Yeah. So I guess so to stay resilient, I usually do three things. So I deliberately reframe rejection as information, and so like we always get critiques or reviewer comments. So they tell us what to improve on. I try to take that and learn from it, but I don't let a reviewer define my worth. Second, I celebrate small wins. So like getting good data from an experiment, submitting a grant, no matter if it got funded or not, just the process of going through all the work to submit it, and even like with the NIH, getting a grant scored, that's I try to celebrate those and build off that momentum, because I think those incremental successes sustain momentum toward the big goal of improving, over time. And then third, I keep proper perspective of reminding myself of who I am outside of science, outside of the lab. So I'm a first generation college student, and so I can look back and celebrate all those accomplishments that matter beyond in any single grant review or result I get in the lab. And also it helps to have a supportive family that's around to kind of help me deal with those setbacks.
That's nice. I like these. I wrote them down so I can try to keep them as my mantra.
Yeah, it's helpful during these difficult times to get funded. So yeah. So let's put on a positive spin. And so we're celebrating Black History Month. And so it's important to look back at the institutions that actually built leaders like yourself. You did your undergraduate work at Morehouse College, a legendary historically black college and university. And so, how did that environment shape your confidence and your approach to science before you move on to your other endeavors at higher level institutions?
Yeah, so Morehouse shaped me in two powerful ways. So intellectually and personally. Um, and both of those mattered when I went to additional further training at Yale and Harvard. Academically, Morehouse has a rigorous biology program, and it has a culture that expects excellence.
Yeah.
So being surrounded by talented classmates who kind of pushed me to develop strong study habits, discipline, and confidence to tackle hard science courses. So that preparation, I would say that helped, that made the jump to, Ivy League graduate school and postdoctoral training much more manageable. So you mentioned the leaders that came out of Morehouse, and so yeah, equally important about Morehouse was the school's emphasis on leadership and purpose. Um, and I think it's hard to find that at most other schools. Um, at least as a black man, finding myself in this world. So Morehouse, saying that Morehouse doesn't just teach subject matter, but teaches Black men to know their self-worth, to understand our history, and to use our skills to make a difference in society. And so that message, reinforcing that message, it gave me the courage to claim space in academic science and, feel like I belong. And so in my current position, I feel like I have two responsibilities. The first is to do excellent science, and then the other is to advocate for a fairer system that gives everyone a chance to participate. And so I think that's what our Morehouse's most famous alum, Dr. Martin Luther King, would want. And also I have to give a shout out to that Morehouse Boston University connection that I share with Dr. King.
Yeah.
Oh yeah. That's awesome. I mean, so community sounds like it's incredibly important, right? And at Morehouse and beyond, I'm assuming.
Yeah. And yeah, I think part of that was, just inspiring the confidence. So at the time I was at Morehouse, I don't know if the statistics are the same now, but when I was there, Morehouse produced, it was the number one producer of Black men that went on to medical school. Um, so, seeing when I got there as a freshman and I saw all these seniors that were, getting ready to matriculate medical school at Harvard and Yale and some of the top places, that inspired me that, a, 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 a young Black man from Mississippi, it inspired me that I could potentially do great things. So,
and you are. That's amazing. Yeah, I love that. Representation is so important, and it's nice that you got to see it. That's awesome. So given your background and your what would we call it, being an alum of Morehouse, and how important and difficult it is to enter the biomedical field without this sort of support, how do you make a concerted effort to welcome diversity in your research team now? You mentioned you're a PI, which many of our listeners already know what that is, but that means that you're the head of your lab. This is the Jones lab. So how are you working to sort of welcome that?
Yeah, thanks for the question. So yeah, as you mentioned, representation is important. And I think one of the biggest issues I faced early on was this imposter syndrome. And like I said, seeing successful people at Morehouse, and then just acquiring confidence over the years in my preparation through my biology courses at Morehouse, that really alleviated most of that imposter syndrome. But it is a real thing, and so I try to make a concerted effort to um, mentor students who are underrepresented. So, as we all do, I mean, I welcome all people of all backgrounds to my lab, but I feel a special responsibility to give back, like to the programs that open doors for me, because I got interested in science because of a summer program that exposed me to biology. So I'm sure you may have heard of this quote. I don't know um, who made this quote, but I can, it resonates with me. Saying that talent is evenly distributed, but opportunity is not. And so that conviction drives my active involvement in helping to develop the pipeline. As I mentioned, been a mentor. I've mentored students from different programs designed to expose them to science, and hopefully, by them seeing me as someone that could overcome all these obstacles, like first generation college student, poverty, all those things. I think that I hope that that will give them hope and inspiration, that they could pursue their dreams. And so it may not be science. There are so many different careers where they could be they could find success and find something that they enjoy doing. But I think part of that mentoring is connecting them with people who can help them figure things out or help them get to where they want to be, and to build those social networks that could sustain their careers. And so, also another benefit of welcoming people of different, backgrounds in the lab is, just as we talked, how engineers bring different questions and methods to a problem. I think similarly, team members from different lived experiences, they bring, new hypotheses, new approaches to experiments, and different ways of interpreting data. I think that makes science more robust.
Yeah. No, I definitely agree that having different perspectives and different backgrounds just informs your science and your approach, and maybe even someone has an engineering brain innately and they can come help solve these biological problems. So I think that's very accurate. And I want to echo the mentorship aspect and how important that is. It is hard and it takes time. So I'm really glad that you're still mentoring others, especially now, because I imagine PI-dom as you don't have enough time in the day to do everything. But
Yeah.
I find it beautiful that you're giving back to help the next gen.
Yeah. Yeah. No, mentoring is I think, a lost art. I think there are so many pressures and demands. And I also think that, I don't know if you've heard of this phrase, the black tax.
I've heard of
You've
minority
heard of
tax as
Yeah,
yeah.
yeah. You could say minority. Yeah, minority tax. That's
Yeah.
more broad.
Mhm.
But I think a lot of times minority researchers, minority PIs are asked to do these things, but
Yeah.
and also students, trainees gravitate towards minority PIs because they want that connection,
Mhm.
and I can understand that. I think, when I went through graduate school, postdoc, I kind of wanted someone that looked like me that, I could relate to talk about the challenges that I faced outside of science. And so I think that's just part of the territory. But I think as it takes a village, not just minority PIs, but others as well to, participate in mentoring.
Yeah. Yeah.
No, that's valuable. And thank you for sharing, Dennis, because it's something that we resonate a lot. I mean, we just heard from one of our last episodes where we had Hispanic Heritage Month, and we were able to talk to Ramon and Alejandro that matched together in a very coherent way out of fate and serendipity because he was looking for a different position in a different lab and he got mixed up. So I think the opportunities come, and as you said, like the people gravitate towards that. But it's also because you want to have a sense of again, feeling represented. And I think that's something really important that we try to give a message to.
Yeah.
So we're going to give a break about the science, and we wanted to give an opportunity to talk to you a little bit about what do you do when you're not just bound to the desk or to the computer, right? So when you need to unplug from the data, the grants, papers, what is your go-to activity to recharge? And do you find that stepping away sometimes helps you come back even better with like more fresher ideas?
Yeah, I mean, you probably know this, but it's hard to like disconnect from science.
Yeah.
Um, so yeah, if you would have asked me this a year ago, I would have said I had no hobbies, um, because I feel like science like dominates everything. But you know, yeah, for a long time I couldn't point to a single hobby, but eventually, I think over the course of last year, with all you know the turmoil going on, uncertainty, I decided to, well, I think that there was a lot of stress involved, but I decided to make room for things I enjoy outside the lab. And so I've always liked sports, watching sports, going to, you know, sporting events. But these days I'm an assistant coach on my daughter's fifth grade basketball team.
Nice.
Oh,
So,
fun.
so I have a new title, Coach Dennis.
Oh, I love
Um,
it.
yeah, so that's a lot of fun, and it's a great way to stay active with family. Um, so I think after the season is over, I'm gonna have to find something new,
Yeah,
on
Yeah.
a week-to-week basis.
I have to say I've
Yeah.
done it tremendously, and I find it incredibly reassuring. I've done coaching for different sports through all
Uh-huh.
my kids pre-K, K, and all the way. I was just
Oh,
their soccer coach,
wow.
and you when you're done with it, I thought it's like, oh yeah, it's gonna be so nice. I don't have the pressure anymore. Now I crave it. I crave being there. Like I miss it. I'm like just
Uh-huh.
looking at like the calendar, like because it's not just mentorship. You get what you were mentioning about mentorship. You get mentorship, but then you get a second chance to look at kids grow and also how
Yeah,
your kid interacts with each other. And then they're in a secure spot because you know that they're getting coached in the right way. You're using
exactly.
good opportunities to actually engage in social activities with them and your kids. So it's great, but it is time consuming and demanding. But I find it that I need it now more than ever.
Yeah, yeah. And so, yeah, those are great points. So yeah, I try to get back to having these hobbies. So when I was in graduate school, so speaking of sports, I was the intramural director for sports. And so I organized the games between like the law school and the med school. And I also played on an intramural team. So those are
Nice.
things I've done in the past, and I want to get back to those, to just,
Mhm.
have those hobbies because they're helpful. So I would say, like you mentioned, taking a break and coming back with fresh ideas. I think the times when I can disconnect, it tends to be like, when I can step away for longer periods, like family vacations. And
Yeah.
Yeah.
so my family usually goes somewhere with the beach that has a beach, to relax, and there I can recharge and kind of come back somewhat refreshed.
Nice.
That's great. I love that. And I can understand why you'd want the beach, especially right now, because we're smack dab in the middle of
Mm.
winter with
Yeah.
lots of snow.
Yeah, so my wife is actually from the Caribbean.
Oh, nice.
Yeah, and so we always go there, December, January, and
Hmm.
it's a challenge to to come back to the
It's
Northeast.
hard. That's the best time to go too. So it's it's the best. That's
Yeah.
awesome.
For sure.
That's
Yeah.
amazing. Yeah. I love the Caribbean. I grew up in Venezuela in Maracaibo, which is like in the Caribbean part of Venezuela. So
Okay.
all right. So
Nice.
Dennis, it was so fantastic to have you on the podcast. Thank you for joining us. I want to thank you for your time today. I know it's Friday afternoon and you gotta rush off to do all the fun stuff like coach and write amazing science papers. But before we end the episode, I want to give you an opportunity to sort of plug or promote any sort of papers or talks that you have in the pipeline for your lab. So this virtual floor is yours.
Okay. So one thing, we have a paper that should be coming out soon. So I talked about the matrix as a barrier for T cells getting into tumors. So we have some new work coming out showing how the extracellular matrix actually affects T cell function. And so we will have a paper coming out soon on that. And then one other thing you mentioned at the top of the podcast. So I was fortunate, honored to be the recipient of this year's Cotran Early Career Investigator Award that's given by the American Society
Congrats.
for Investigative Pathology. And so you can find me at the annual meeting in Fort Myers, Florida in May of this year. And so hope I see folks there.
Yeah.
Yeah, I'll
That's
definitely
exciting.
see you there. I'm excited. Well, thank you so much for joining us. For our listeners, we will have information about Pathobiology 2026 in the
Yeah.
summary of this episode.
Yeah, we'll have a lot more information. And thank you, Dennis, for the time. We want to remind our listeners because we do have an upcoming mini-series, a 3-part mini-series, where we're going to be engaging one of the topics that actually you just mentioned about unwinding and the pressures about not just research, but in general. So we're going to have a 3-part mini-series that is going to be split and starting March about the biological cost of trauma. And so we know that trauma isn't just a memory, it's a biological event. And so this 3-part mini-series, we're going to be investigating how trauma rewrites our biology. And we're going to go from cells to city streets, going from the research that happens for this all the way through how our community engages in this. And so we're going to be talking to different leaders and scientists fighting to heal the invisible wounds. And sometimes that affects a lot of our heroes, people that are devoted to our safety, our military personnel, people that suffer from this cognitive impairment issue. So we also have journal highlights for the American Journal of Pathology and the Journal of Histochemistry. And so for everyone listening, thank you guys for listening. And we'll see you guys in the next episode.